G'day, welcome to McCrometer's Mining and Minerals Processing webinar. We're going to talk about flow measurement in the mining and minerals processing industry. My name's David Splatt. I'm McCrometer's Asia Pacific Manager and I'm based in Perth, Western Australia. I've had the privilege of supplying field and control room instrumentation to the mining industry for over 40 years. Today's webinar will start with a brief introduction of McCrometer and follow with a high-level summary of the current mining industry challenges. Then we'll introduce McCrometer's mining industry flow meters, and finally we'll discuss how McCrometer's products address common challenges. McCrometer is part of the Danaher Corporation. Danaher are a Fortune 500 company with over 79,000 employees. Our current market capitalisation is $200 billion. Danaher are a global science and technology company providing innovative solutions to the markets we serve. Following on the innovative theme, McCrometer specialise in design and manufacture of many unique metering solutions for a wide range of applications and markets. All of McCrometer's products are manufactured at our factory and head office in Hemet, California. Supporting our head office is our large flow test facility in Porterville. Porterville is just north of Bakersfield in California. Our Porterville facility can flow test meters up to 48 inch. That's 1.2 metres in diameter. For the FPI users, which I'll introduce coming forward, we can do meters up to 3.5 metres in diameter. We support those products worldwide through our carefully selected channel partners. Each of those channel partners is supported regionally by a McCrometer manager who is, in his own right, a flow specialist. Whilst I have 40 years experience in the mining industry, I thought it would be prudent to do a reality check on the current challenges when preparing for this seminar. Found the key challenges hadn't changed, just perhaps some of the weighting of those challenges. So what are those challenges? Lower grade ores call for more efficient practices. More complex processing adds to production costs. Operators focus on cost reduction to maximise profit and shareholder value. Energy conservation saves cost. It helps them meet their environmental licences and makes for a good corporate citizen. And we all know no minerals processing occurs without water. Water management is often key to a project's success. Many disciplines come together to make a mining project. Each discipline plays its part in meeting the project's goals. Flow measurement plays its part by meeting unique and often challenging flow conditions. Distorted pipework causes disturbed flow. Installation points may be high up in a building or very remote. Erosive and corrosive fluids may cause their own issues with materials of construction. Equipment is always bought with maintenance in mind. Accuracy and repeatability changes from application to application. Permanent pressure loss is lost energy and adds to issues when product needs to be delivered to a vessel at a particular pressure. Emergency shutdown systems may be required around burners and gas compressors and other items of equipment. Project location and geographic area could be a challenge. Some tenements may be as large as 1,000 square kilometres. To address these challenges, McCrometer have 4 technologies I'd like to talk about. In 1955, the McCrometer company was formed by Floyd McCall and Art Crom on the back of the propeller meter. The propeller turns a cable, which then is connected to an indicator at the top of the meter. The beauty of using a cable instead of gears to transfer the rotation of the prop is there's nothing to shear. To add to its durability, there's a magnetic coupling between the propeller and the cable. If there's a surge of water down the line, the propeller rotates quicker than the magnetic coupling, breaking the coupling and allowing it to free spin until it grabs again. This protects the meter in the most difficult of applications. The propeller meter is available in a saddle style, as shown here in the main drawing, or as an inline version, as shown up here in the top right. I've now got a couple of slides introducing McCrometer's range of electromagnetic flow meters. For those of you unfamiliar with the principle, I draw your attention to the image here in the top right. Here we've got a piece of pipe with a couple of coils around the pipe generating an electromagnetic field. The conductor, shown by the blue line, is the process fluid. As it cuts the lines of magnetic flux, it generates a voltage proportional to the velocity at which the conductor is cutting those lines. As we know the velocity and the ID of the pipe, we can then calculate the flow rate through the meter. Thank you, Mr. Faraday. To the left here we have McCrometer's Ultramag flow meter, and to the right we have McCrometer's Duramag flow meter. The Duramag is battery powered. McCrometer's mag flow meters utilise our ultraliner technology. Ultraliner is a fusion bonded epoxy which coats the entire meter. The beauty of this technology is that you don't get any liner delamination, making it ideal for the mining industry. I'd now like to introduce our innovative range of insertion style mag flow meters. We have two broad families, hot tap and saddle mount. Here we have the hot tap version with the FPI full profile insertion mag flow meter and the SPI single point insertion mag flow meter. The principle of the FPI can be seen up here in this right hand corner, where we have the probe passing right across the pipe to the other side of the pipe, and various coil and electrode assemblies within that section to capture the flow rate all the way across the pipe. The single point just sits in the wall of the pipe. Shown not so well in this slide, but addressed later in the presentation, is our saddle mount version. So our saddle mount version of the FPI could be considered this McMag 3000. Whilst it can't be hot tap installed, all we need is a hole in the top of the pipe large enough to pass the meter through. And finally, I'd like to introduce McCrometer's unique V-cone differential pressure flow meter and its baby brother, the wafer cone, shown here. Like all DP outflow elements, the V-cone needs a DP transmitter, but that's where the similarity ends. The V-cone is very unique in that it offers solutions to many mineral processing plant challenges. It's self-conditioning, doesn't need any up and downstream straight pipe. It's self-cleaning, making it virtually maintenance-free. Its in-service life expectancy is 25 years. It has a low permanent pressure loss. It's accurate at plus or minus 0.5%, and we've done turn downs of as much as 50:1, maximum flow to minimum flow. It can be manufactured out of a variety of materials to handle erosive and corrosive applications. So, having introduced the flow meters, let's look at each of the challenges. The disturbed flows caused by elbows, tees, valves, other pieces of plant that make it difficult to get an accurate measurement, often requires rerouting of the pipework to get the straight pipe requirement to get an accurate measurement. Well, the solution to that is provide a flow meter that can measure accurately within a minimum straight pipe run. So let's look at how McCrometer managed disturbed flow. The V-cone to the left has been tested to API 22.2 to establish its up and downstream straight pipe requirements. Those requirements are published in our manual and on our website, and the table there shows numbers like 1 diameter up and 1 diameter down for disturbances such as elbows and elbows out of plane. On the right hand side we have similar testing for the FPI and a similar published table, and a sample of that table is there. It shows things like 0D and 0D for some disturbances and as much as 5D or even more for other disturbances. We can be very specific with the up and downstream straight pipe requirement if you can share your piping layout. For those applications where the FPI or the V-cone aren't suitable, we also have our range of retrofit McCrometer flow conditioners. The basis of the flow conditioner is a cone. That's because the V-cone is self-conditioning and offers a self-conditioning effect in its own right. The next challenge we're going to discuss is installation. Lots of flow meters sit between flanges. Sitting between flanges requires a pipe shutdown, dewatering and depressuring in order to install it. Larger sizes and heavy lifting may be required. If it's up at a high level, then there may be some scaffolding and other issues involved. Because the solution is a flow meter that can be installed without shutdown. If shutdown is required, the faster the installation, the better. If shutdown is unavoidable, then a meter that doesn't require maintenance would be perfect. Let's start with meters that don't require shutdown for installation or removal. The FPI full profile insertion mag flow meter and the SPI single point insertion mag flow meter offer 0.5% and 2% accuracy respectively. Both meters are installed through a 2-inch ball valve. So we mount the meter on the 2-inch ball valve and ease the probe towards the ball of the valve, opening the valve at the appropriate time, allowing the probe to pass into the flow stream. In this manner, the fluid can remain under pressure at all times during the installation. A cost-effective solution for feed water and process water around the plant are our saddle-style meters. Saddle-style meters are installed by cutting a hole in the top of the pipe and clamping the saddle into place. We have a mechanical solution, shown by the prop meter, and 2 mag flow solutions, both battery powered. The next challenge I'd like to discuss is erosion. Whilst I'd like to acknowledge the place that slurry plays in this field, I want to focus on dirty gases and steam, as I found that some of the plants that I worked on in Western Australia had issues related to erosion in these areas. Of course, the solution is to design a meter that resists erosion, or design a meter where the geometry inherently avoids erosion. The V-cone measures liquid flows very well. It also measures gas flows very well. Dirty gases may be travelling at quite high velocities and be quite erosive. The purpose of the image to the right is to show how the particulates are directed away from the measuring edge being this part here. And therefore, if there's no erosion to the measuring edge, then there's no change in the geometry of the meter, and then therefore no change in the accuracy. To assist that, we also take advantage of the boundary layer effect. The boundary layer is where the molecules of the flowing fluid stick to the surface of the cone at a molecular level, and as we move away from the cone, the velocity starts to increase. The boundary layer is thought to be at its maximum at the beta edge here, thus providing additional protection to the measurement and allowing us to offer a 25-year in-service life. Earlier, I'd indicated that the V-cone is self-cleaning. The image to the left shows an orifice plate after 3 months service on a gaseous application. Below that is an image of the V-cone on the same gaseous service after 9 months operation, still pristine and clear. Some users may be concerned that that level of dirt, even though the meter is clean, may block the tapping points for the flow meter. McCrometer have some solutions there. We can put enlarged tapping points in our meter and sense the pressures with diaphragm seals. This overcomes issues where the client may be concerned about blockage of tapping points. Earlier I mentioned that the beta edge of the cone, that's the measuring edge that you see there, is protected by the angle of the cone deflecting particulates away from it and the boundary layer effect. Nevertheless, we were interested to understand what accuracy shift we would see if the cone edge was damaged. The graph below that shows before and after flow test, where we can see that the accuracy shifted by about 0.6%. For those applications where client wants a belts and braces approach, we have the ability to tungsten coat or other materials our flow meters. The V-cone shown on the right there was actually for buried service, and the client wanted to be sure he was going to get no erosion. The next application challenge we're going to look at is corrosion. Corrosion can occur from within the pipe, or it can occur from the atmosphere around the pipe, or it can occur from hypersaline water washing down the plant. The solution, of course, is to design flow meters out of wetted parts that resist corrosion. That becomes more difficult as we look at some of the more complex minerals processing plants where titanium may be needed. The ability to manufacture a flow meter out of exotic materials will help solve this problem. McCrometer have a 40-year history of manufacturing V-cones out of exotic materials. This is not a problem for us. Duplex, super duplex, all very common. Incolloy, Monel, titanium. If your plant needs it, we can build it with that material. Let's now take a look at accuracy and repeatability. Sometimes accuracy is important, sometimes it's not. Accuracy might be important for fiscal transfer, might be important for environmental monitoring. Repeatability may be important for PID control loops. Important solution is to find a flow meter that meets the budget at the accuracy required. Here's a table of the accuracies of the flow meters that we've been discussing. I'm not going to go through the table in detail, but I would like to draw your attention to the options that you have with each installation style. Here we have the FPI hot tap insertion mag flow meter and the SPI hot tap insertion mag flow meter. You select the accuracy that suits your needs. Similarly with the Duramag flanged meter and the Ultramag flanged meter. Also the saddle style, McMag 2000 and the saddle style McMag 3000. Whilst on this page, I thought I'd drop in a graph that we could supply to our clients who want to know what the accuracy will be at any particular point in their flow. This is something we do commonly for our clients. Now we're going to talk about pressure loss. Pressure loss is caused by obstructions in the pipe or even friction losses along the wall of the pipe. Pressure loss is lost energy. Many processes require that the fluids delivered to a vessel at a particular pressure. Pressure losses almost always must be accounted for. With some flow elements, turn down versus pressure loss is a delicate balance. The solution, of course, is to find flow meters with minimal intrusion that will reduce pressure loss. Flow meters with designable geometry can also be used to balance the turn down versus pressure loss requirements. The gold standard for minimum pressure loss is obstructionless metering. The mag flow meter is an obstructionless flow meter. Look down the centre of the pipe of a mag flow meter, there's nothing to see. Coming close behind the inline mag flow meter is McCrometer's single point insertion mag flow meter shown here on the right. As you can see, its nose barely protrudes into the pipe. Following behind that, the McMag 2000 saddle meter, McMag 3000 saddle meter, and FPI full profile insertion mag flow meters are also low permanent pressure loss designs. Now we're going to talk about permanent pressure loss relative to the V-cone. The V-cone is a differential producing flow element. Like other differential producing flow elements, it utilises Bernoulli's theorem of conservation of energy. Bernoulli's theorem postulates that energy within an enclosed system, like a pipe, can't be created or destroyed, it can only change state. So, as the flow approaches the V-cone, it has a certain amount of kinetic energy and a certain amount of pressure energy. As the velocity increases as it approaches the cone, the kinetic energy is increasing, therefore the pressure energy, to make the equation equal, must reduce, and that's what we measure as the dP there. As we pass the cone, the velocity decreases, in other words the kinetic energy decreases, so it gives off some energy back into the pressure energy, so the pressure increases. So the permanent pressure loss across the cone is this small amount here, whereas the measured dP is this amount here. With the V-cone, we can change the size of the cone to suit the process requirements. Less permanent pressure loss, reduce the size of the cone. More turn down, increase the size of the cone. That's why we have claimed that the V-cone has designable permanent pressure loss. Let's take a look at safety instrumented systems. An emergency shutdown system is a protection layer which takes action to shut down a plant should it enter a potentially dangerous state. It should operate independently of the plant's normal control system, and it should provide redundancy calculated to meet the risks of that dangerous state. The solution, of course, is electronic flow meters certified for functional safety requirements, IEC 61508 in my region. Mechanical flow meters aren't covered by that standard, so it is incumbent upon the manufacturers of mechanical style flow meters to design meters to meet the intent. McCrometer provide V-cones for safety instrumented systems. Such V-cones include one process tap, which is those taps there, and one set or two sets, or you can barely see it there, 3 sets of taps for the emergency shutdown system. The purpose of the multiple taps is to provide confidence voting during an emergency event. Discussion on the challenges so far in this webinar logically lead to a discussion on maintenance. Maintenance is costly. Maintenance is lost production. Unscheduled maintenance can be expensive. Flow meters that are easily maintained are an advantage. Flow meters don't require maintaining at all are an even bigger advantage. McCrometer expect a 25-year in-life service for the V-cone. How do we achieve that? What's the evidence? On the right-hand side, we can see images of a V-cone on coke oven gas. This is extracted from a paper by the user of the cone who had used vortex meters on a similar application with no success. Here you can see the V-cone area is self-cleaning, whereas the approach pipe work is coated by that dirty, sticky gas. To the upper left, we see testing to MIL S901. For meters to be used on naval vessels, they must pass this standard, which includes blowing up the meter a number of times with a 60-pound charge. The meter is then tested for structural integrity and operation, and only then can it be used. V-cones are used by the US and British Navies. The evidence of this is also anecdotally in our ability to supply these subsea. The bottom left sees a subsea chemical injection meter. The two cylindrical components poking from the top of the meter are super duplex stainless steel housed DP transmitters. With a 25-year life for our meter, the weakest link in the chain is the DP, so two are supplied for redundancy purposes. Having spoken about the maintenance-free V-cone, let me now talk about the easy-to-maintain FPI and SPI insertion mag flow meters. So, I've already discussed the ability of the FPI to be installed and retracted under pressure. In this image here, we've got a couple of gentlemen who are probably installing or maybe removing an FPI for inspection. You can see there's some long rods here. Those long rods are designed to allow the meter to be retracted from the line under pressure without the meter shooting out and hitting anybody in the chin. Once the meter is retracted past the ball valve is closed to isolate the meter. Maintenance is a breeze. Last of the identified challenges was project location and geographic area. Ore bodies aren't always situated in convenient places. Some tenements, as I've already mentioned, are over 1,000 square kilometres. That makes getting power to and feedback from remote locations a problem. Mechanical and instruments with long life batteries will solve part of that problem. And of course, we need to have some way to transmit those flow readings back to a central location. McCrometer have a suite of battery powered flow solutions. On the left hand side, we have our saddle solutions. And on the right hand side, we have our DuraPro inline full bore mag flow meter. And then our SPI and FPI mag flow meters with the battery powered Procom converter option. Typically, we expect 5 to 7 years battery life out of each of these models. Hot battery replacements available without loss of data. Of course, there's solar options if you like that. And local output options include frequency pulse, 4 to 20 milliamp, and some telemetry options. Remote transmission options include a pulse output per unit volume, frequency output, our Flow Connect, cellular or satellite solutions, McCrometer Connect telemetry on the left-hand side there where we can see our telemetry unit with the solar panel, and smart outputs available on most meters. Not mentioned earlier, but other challenges on some projects are high pressures, high temperatures, large line sizes, wet gases, steam, dirty steam, wet steam. The solution there is meters designed for the application. Large line sizes aren't a problem for McCrometer. Got a couple of images of V-cones on the left there, fairly large V-cone. The top left, fairly large cone. Don't be put off by the size of the cone. As I mentioned earlier, we can change the cone size to suit the requirements of the application. And below that, an image of another very large cone headed for Sweden as flue gas measurement. To the right, we have our FPI solution. It's about 128 inch. It's at 3.3 metre FPI, getting ready for installation at the City of Boston. And just to show that we also do the small, there's a 15mm V-cone in the centre. McCrometer regularly design V-cones for high temperature or high pressure applications. The minerals processing industry often sees calciners, autoclaves and roasters. All of those may have hot gas measurement applications. In the centre here I've got the photo of a V-cone taken at an Alcoa site near me. Note that the flow is from right to left, and the client commented that they struggled to find a flow meter that could handle the temperature, 400 degrees C, the pressure, minus 0.3 kPa in such a short pipe run. McCrometer also supply high pressure V-cones for a number of applications. We regularly build meters with API 10K flanges. I think recently this year we received an order for several 20-inch meters with API 10K flanges. Hub connectors are also common. A little over 20 years ago, McCrometer decided it would be advantageous to understand the performance of the V-cone on wet gases. These videos were taken at Southwest Research Institute in San Antonio, Texas. They show 5% liquid fraction travelling along the bottom of the pipe. Interesting to note the mixing effect or self-cleaning effect of the V-cone, drawing the moisture off the wall and transporting it down the pipe, effectively keeping the metering area clean. In contrast to the right, we can see an orifice plate from different angles on that same surface. The top video, you can see the liquid fraction clearly jetting over the edge of the plate. This would be an area for erosion. We can also see a recirculating area there, where the liquid fraction is being drawn back to the downstream tapping, thus explaining why downstream tappings often are the first to build up with liquid on wet gas applications. Steam is often used around a minerals treatment plant for heating. The V-cone is a preferred solution. It offers self-cleaning. Its low permanent pressure loss ensures that the steam remains superheated for longer, and with the geometry of the cone sitting in the middle of the pipe, condensate passes by easily. Scale and other solids passing along the line don't affect the meter, as we've already shown its immunity to abrasion. Well, that finishes the webinar. Hope you found it interesting. Here's a summary table of the features and benefits that I shared with you. Supply this so you can easily select the correct flow meter for your application. Thank you for watching this webinar. Unfortunately, it's not possible to do justice to some of the content in a 30-minute time slot. If any of the information I've shared sparked any interest, please contact your local McCrometer representative or McCrometer's regional sales manager at these links. Cheers.